Fatima, as you are aware, she's a master's student in MME program. And also at the same time, she's design engineer intern at Tinker and Racer. She has been very active member of SME, SUI, and IISC. She has a very good academic standing, 4.0. And also, she attended several conferences, competitions. The latest one was a couple of months ago, or last month actually, at AeroDev. She won the top award from SME event among all graduate students. And she has been already accepted to PhD program, MSec, at Texas State. So she's gonna start in fall 2020. Also, she received very prestigious award with her admission. Is Texas State Doctoral Merit Fellowship, I believe is $9,000 or something like that. So she's rich as well. And she's very hardworking, good artist. She's married and also raising her child at the same time, already published a couple of papers. So she's a fighter in multiple fronts. So she's gonna do the last part, which is her thesis in here. Fatima,
okay,
back to you.
That's a lot of introduction. Okay, so I'm gonna start straightforward. My thesis title is Design and Development of an Integrated Water System, combining rainwater harvesting system and atmospheric water generator. So under this presentation, I'll be talking about some problems, potential solutions, hypotheses under introduction. Then under each hypothesis, I'll talk about some literature highlights, methods, materials, and their results. And I will conclude with the conclusion, future work, postgrad plan, and my references. So the problem. Scarcity of fresh water is a global problem. In 1995, the world population was 5.7 billion, and the orange color on the figure shows that the regions that had more than 40% water withdrawal. The prediction for 2025 with a population of 8.2 billion shows the extension of these areas. The overall water withdrawal has been increased around the world. So currently, 1.2 billion people do not have access to safe water, and 40% world population faces water scarcity each year. The animation shows you the water cycle on the Earth. The table on the right shows how much percent of total water belongs to each type of reservoir. Majority of the Earth's water is either inaccessible or cannot be used as fresh water. Only this little percent of water is in the streams and rivers, which you can use. And in the biosphere, we have a very little amount of this water or moisture. So 91% of evaporated water returns to the ocean by rainfall, and only 9% rainfall occurs over the land masses. So our focus is kind of solving this water scarcity problem. First potential solution can be atmospheric water generator, or in short, AWG. It's off-grid water, and the reason I'm saying off-grid water is that this means it is not connected to any municipality water network system, especially if this is good for the remote areas where people do not have access to safe water and the place is too far from the developed areas to establish a water supply line. That's why. So this water is free in terms because it uses the surrounding atmospheric moisture, but it's energy intensive to run and inconsistent in nature because the production largely depends on temperature and relative humidity of the atmosphere. This device is, the idea is taken from biomimicry from fog beetle, which you can see in this picture. And in this video, you see a Namibia desert beetle that can condense moisture from the fog. So it stands like this, and it has hydrophobic and hydrophilic, both kind of skin on it. So the hydrophilic attracts the moisture, and the hydrophobic let the water run towards its mouth so it can drink it. So this is how the atmospheric water generator, like the inside schematic looks like, and the water components are shown here with the numbers. So basically the air flows in with the help of air filter. It's filtered, then condensed, and then reserved in the bottom reservoir, then passes through a set of filters to the top reservoir to ready for supply. And this is how you push a button and can have the water out from the AWG. And the second potential solution can be rain harvesting system, or in short, RHS. This is also off-grid water. And this is free because this is a natural phenomenon, but unpredictable and variable in amount. Another problem we have is how we use the water, especially the fresh water. On average, 70% fresh water is used for agriculture over the world. And by 2050, there is expectation that 50% increase in cultivated production and 15% increase in freshwater withdrawal will be required. So what can be a potential solution for this problem? A vertical farming is a good solution because this is off-grid farming, and this is called off-grid farming because it doesn't require land. It doesn't have to be connected to any land facility, something like that. Directly, it's not grown on land, it's grown on controlled environment, and it uses only 20% water if it's compared to the conventional farming method. And this is basically hydroponic farming, and the reason it's called vertical farming because it's placed vertically to utilize the space. And hydroponic is growing plants in nutrient solutions, and the way you see in the picture. And it has some other benefits like this, on twice growth rate, nutrition efficiency, fewer pesticides, something like that. And so this is the reason that I'm using our evergreen project of vertical farming system in the Freeman Center to be the application site for my smart integrated water system. And I designed it accordingly. So I have 5 hypotheses about this project. So in short, I'm just gonna tell that the first one is if we integrate this rainwater harvesting system and AWG, then it brings consistency. And then addition of a smart AWG brings more stability. This integrated system can perform automatically and is superior in quality when in terms of water quality and integratability. And in the fifth, that if for every location and demand, the size and capacity can be calculated. This is just a literature overview to show show my novelty of work. There are literatures where these different RHS, AWG, or different terms were discussed. Sometimes rain was combined with dew, fog, or potable water, but not with AWG. And my work combines all of this. So hypothesis 1 and 2, it assess the feasibility of integrated system. And the reason I put those 2 hypotheses under the same umbrella because for these 2 hypotheses, the method and materials are same, except for the results. So literature highlights for rain harvesting system. In this figure, you can see that by the red zones over the years from 1986 to 2016, the rainfall amount has been increased, especially since we are in Texas and working with the data from San Marcos. It is important to observe that the total precipitation has increased in Texas, as you can see in the red zone. Widely used water source and the rain harvesting system, then it is found that 87% savings of supply water is possible. The system is 93 to 100% reliable. And this is particularly popular for outdoor water uses when you don't need filtration or something. And it's sufficient for non-potable demand in arid regions like in Arizona and Texas. And design parameters depend on region based, of course, because of the rainfall pattern. The highlights for AWG. So this figure shows the fraction of favorable time for AWG based on meteorological data from 2005 to 2014, combined with water scarcity map. Around the world, majority of the places that were estimated shows that the favorable time is more than 50%. Especially focus on Texas here again. So in Austin, Texas, it's about 70%. As I mentioned earlier, the AWG production depends on atmospheric condition. So this work is done by Dr. Baramashia Banpur. So here in the graph, you can see the humidity in this axis and in this axis temperature, and this is on the y-axis. On the vertical axis is the water production. So the red zone is the area of high production, which is usually when the temperature is greater than 60 degrees Fahrenheit and relative humidity is greater than 40%. And this is also a better alternative when we operate this with renewable energy. Methods and material for these hypotheses is data collection, catchment area calculation, feature scaling, coefficient of variation calculation, graphical representation, and interpretation. I'm gonna explain these steps in a few minutes. So the data collection for RHS, precipitation. So this data was collected directly from NOAA, and the data was collected for 2014 to 2017, this 4 years of data. And the data comes as in inch, like daily precipitation. For January 7th, there was no rain. January 13th, there was 0.4 inch rain. So when we multiply this inch of rainfall with catchment area, we get the volume of water that we can collect. This is our rain harvesting system in Freeman Center. You have the rain gutter system is here. So this is our catchment area, and this is the measurements of catchment area. The data collection for AWG was taken by team members at Freeman Center from the same amount of time for 4 years. And since this is collected directly in this lower tank, so we get the volume of water directly from here. And this is just a sample of how the data looks like. Next is feature scaling. Feature scaling is done because it's easy to, because when it's done, the values are converted in between 0 to 1, and it's easy to compare both systems in single plot because usually the AWG production is way less than the rainfall production. Suppose this highest rainfall was 68,000 liter when the highest rainfall for the highest AWG was 800 only liter. So that's how it's calculated with this formula. And these are the reason that we did this feature scaling. Next is coefficient of variance, which is a measure of relative variability, and is calculated by the ratio of standard deviation and the mean. And a smaller value of CV means less variation, that is more consistency. So as we see in the summary table, this is for rain, which the variation is 1 because it can rain or it cannot rain, something like that. So the highest rainfall or no rainfall. And for the integrated system, rain plus AWG, we get the coefficient of variation 0.51, which is less than 1. So it means that this system has more consistency over rainfall. So the hypothesis 1 that this integrated system is consistent, the claim is accepted. So we put rainfall data and AWG production data in a chart to see the pattern, how it looks like. From the graph, this is the water production index, which is similar to the equivalent to the normalized values of water production from 0 to 1. And here are the months from 2014 to 2017. And you will see sometimes rainfall is up, the AWG curve is down. That means in this time frame, there are several times that rain harvesting system and AWG peak their production in opposite seasons. This leads to the idea of integration of these two systems. So the result, how does it look like, the integrated system? This is the graph, again in y-axis water production index, and here are the months, just denoted by the numbers. So you can see even though in the months when there is no rainfall, there is AWG production. And AWG production is more consistent than precipitation and is possible even when there is no rain because of the atmospheric and temperature condition. So again, we come back to the coefficient of variance table, and this time we see gain plus smart AWG. And by smart AWG, we're saying that AWG will only run when it's necessary and when it's feasible for it to run. So we calculate the CV for here, and we see that 0.44 is less than 0.51 and also less than 1. So basically, this with the integration with the smart AWG, it brings more stability to this integration system. So the claim, the hypothesis 2 claim, we also accept it. Result for this section, that how the smart AWG integration looks like. So it looks like AWG is off when there is plenty of rainfall. Usually the rainfall is above historical average, so we don't need to run this AWG. So as you can see, these places AWG is off, it's not running. And so now this time AWG works only as a backup system for the rain harvesting system. And this can be designed based on the demand and operational feasibility, which I did for this vertical farming system based on the temperature and relative humidity too. So the integrated system automation, the hypothesis 3. Literature highlights are that this is first time RHS and AWG integration is done, and rain is integrated with fog, dew, supply water, etc. before, and automation is done by using Raspberry Pi, Arduino, different sensor and control systems, and algorithms are designed for water pumps, storage tanks, etc. And this is a deep ultraviolet sensor working with the computer and Arduino setup. So I used Arduino for my project. The methods under this hypothesis is concept integration, 3D CAD model drawing, electrical and mechanical component selection, logic development, fabrication, experimentation, and validation. The subsystems and concept integration, the first step. So this is the schematic of the integrated system, which has the RHS, the AWG, the reservoir, the common reservoir. So the way we integrate these two systems is take the subsystem, the common subsystems for those two systems and make them one. And this whole system is divided into two sides, that is generation or collection side, and the other is delivery or consumption side. So the CAD model here shows you the better view how the model looks like. So this is our smart integrated water system. The rain falls on the roof and is stored in the main tank. The AWG generated water is stored in the secondary tank and then pumped to the main reservoir. Water is purified through a set of filters. And finally, this water is delivered to the supply tanks for nutrition solutions. This is the Evergreen project, and we have 8 supply tanks. This is how the water will deliver from this side. Okay. So this is the collection side. Figure on my left shows the logic flow diagram, and figure on my right shows how the power supply connections, the digital signal, water flow is color coded, as you can see. So the system starts working when the primary reservoir has a water level less than 1,000 gallon. This tank is capacity is 3,000 gallon, but when it's below the 1,000 gallon, there is a power supply 10-volt AC power supply that turns on, which basically turns on this whole electrical side. So then the Arduino will start assessing the relative humidity and temperature. So with the atmospheric sensor here. So based on the feedback, if it's feasible to run or not feasible, it will decide to turn on the AWG or keep it off. Then the next step will be assessing the float level from this secondary reservoir. So if this reservoir is full from the water from the AWG, then it will send the signal to Arduino, and the Arduino will turn on the pumps to transfer this water into the primary reservoir. So the relative humidity range that I put in the algorithm is 30 to 100%, and temperature range was 55 to 120 degrees Fahrenheit, and this pump will run for 20 minutes. On the delivery side, this is the logic, and this is the picture similar to the previous one. So the floats, they're in 8 tanks. There are 8 tanks, as you see the array. And so 8 floats, 8 solenoids, and 8 channels. And there will be 2 Arduino, each Arduino controlling 4 sets of solenoid and 4 sets of supply tank, or like the floats. Then when the float gives you the signal of that the water level is down, it needs refill, then the Arduino uses this relay to open the solenoid valve so the water can flow in to the supply tank to refill it. So this is the logic for each float that's working on that low level water. If yes, then it opens, and then delay for 5 minutes. That means the solenoid stays open for 5 minutes.
Not doing the research.
Okay, so since due to this COVID-19 pandemic situation, it was not possible to install this full automation on site because there is some work needed to be done. For example, like lifting the AWG on top of the frame, some plumbing work, installing permanent water lines. So however, this electrical system is tested in experimental setup in this first video, and then this setup was taken to on site for experiment. So there are 4 floats working with 1 Arduino, and these switches are numbered as the floats, and the floats are numbered according to the pins that they are connected to the Arduinos. This video basically showing you that it doesn't matter if 1 float or all the float or multiple floats are giving you the low signal or high signal. This algorithm is able to execute its operation based on that. For this video, I just changed the logic into 5 seconds instead of 5 minutes to make it quick. And on the right side, okay, on the right side, the video, you can see that the whole system from here, the experimental setup was taken into the Freeman Center. And instead of number 7 float, we connected this float with that with the same switch, that same pin. So number 7 is working as in the supply tank. And these are the other 3 floats. They're all in the water level low position. So all of them are turned on and the water is flowing because the solenoid is on now. Then I manually pull up the switch to give the float, it's a water level high signal. It turns off this switch and then water flow stops. So the hypothesis 3, that the integrated system can work automatically and supply water to the point of use, we accept this claim. So hypothesis 4 is water quality and compatibility. As we are, our focus is designing this integrated system for the vertical farming. The vertical farming, the plants especially needs nutrition water. And this nutrition water needs to have some characteristics for the plants to grow in a better way. These are the important characteristics like the pH level, electrical conductivity, composition of ions and amount of chlorine. So in this figure 21, you'll see that at different pH level, what are the composition of the different nutrients that plants can get. And this literature actually preferred the range to be between 5.6 to 6.2. And this is the range, shadowing the black. And on the right image, you'll see the comparison of hydrogen ion concentration as pH between 1985 and 2016, which shows that more green it is, the pH concentration is more. So the pH concentration has been increased in rainfall over these all years. So sometimes people also call it as acid rain in recent years. So this is for Texas. So pH in rainwater has been increased over the years. Electrical conductivity or salinity is the amount of dissolved solids in the water. For the nutrition water, it is the range should be between 1500 to 2500. Composition of ions are these ions, and nitrate and calcium is highlighted because we actually measured these two ions. Amount of chlorine is preferred none to be present in the water, because the presence of chlorine in the water that makes that bonds with other nutrition like nitrate or and ammonia, then it becomes chloramines, which is deadly kind of for the plants. They can kill or hinder the growth of the plants. So it's not recommended in the water. The methods and materials for these sections these are the kits that we used, and samples were all collected in clean and dry jars to ensure that there are no contamination. Testing were carried out immediately, especially for chlorine, because if you keep the water open for some time, the chlorine may get evaporated. And only, I'm pretty sure you cannot see it clearly here, because only the supply water was found to have chlorine, but the others were not, and it's expected, because only for the supply water, they treat the water and put chlorine in it to disinfect. So it was expected. The test kits were calibrated at first and then tested for reading accuracy with standard solution every time. And calcium iron tester malfunctioned, unfortunately, after taking a reading for 2 samples. Hence, I have incomplete results. So let's go to the results, and this is the summarized table for the results. So AWG water and the rainwater has pretty much low EC. pH is near the preferred range of pH. Calcium, nitrate, there are very low amount of them. So we tell that AWG and rainwater is ideal for nutrition control, because when you have this less EC in the water, so whenever we're putting nutrition solution in it, we have better control of whatever nutrition we want in the water or what we don't want in the water. That is why it gives us better nutrition control. Well water has no significant problem, but still the EC is high. There's calcium, but we don't have like 100% control over the other nutrients. Supply water also doesn't have significant problem, but it has chlorine. It's not destructive for the plants with this amount, 1 and 1. So it's acceptable still. The groundwater that is collected from my office in Seguin, which is surrounded by the cornfields, and they put fertilizers in the field. So it's expected that they have a high nitrate amount, it's about 50, and high EC. This groundwater sample actually can be directly used as a nutrition water, but again, we'll have no control over the nutrition composition, but this is not definitely safe to drink. The safest range is until 10, the nitrate level, so it's not safe to drink. Okay, so our fourth hypothesis of that this automated system is can act as a superior watering mechanism for in terms of water quality. We accept this claim. Our hypothesis 5 is design feasibility and a case study, which is Evergreen project. So the literature highlights shows that in case of industrial water networks, mathematical programming based techniques are used, such as you can see in this figure. But ours is a pretty simple system and short, small system, so we didn't use this modeling or something. We used pretty much these design parameters for this. But whatever the system or approach we take, the design focus is to meet the demand, save water, and save energy consumption. And the storage tank capacity is highlighted here because this is the tank capacity we determined at the end of this hypothesis. Methods and materials for this hypothesis is a year-round observation from 2014 was collected for the demand calculation. Graphical representation for better understanding of the seasonal rainfall pattern, and supply demand calculation. We consider 2 vertical farming units. So each one having 8 supply tanks, we considered 16 supply tanks with this existing RHS and 2 units of AWG. Then finally determine the tank size what is needed to run these 2 vertical units. So first we did some rainfall pattern observation. This is the data from San Marcos, Texas climate shows the plot over average, plot for average high temperature for each month. From this plot, we decided to consider these 7 months as summer months that has the temperature close to hot or above hot line shown in red. The rest of the 5 months are considered as winter months. On the right, the graph shows rainfall pattern in 2014 with AWG generation. The graph shows the collectible amount of water in gallons as well as the percentage of water production on y-axis to show how much contribution is done by each system for each month. We can see that amount of AWG water production is actually very less than the rain harvesting system. And also during the summer, the rainfall is way bigger than during the winter. So we had the data for 2015, 16, and 17, and we had the similar observation for all these 3 rainfall pattern observation. So I'm not going to explain this, just to show you the similar observation. So this is the summary table for the results. So minimum demand occurs during winter. We considered 1 gallons per week as minimum demand, and maximum demand occurs in summer, and which is about 35 gallons per week. Available, we calculated this available and achievable amount of storage capacity because we have a currently installed 3,000 capacity of tank. So the achievable is considering that there is no restriction over the storage capacity. So whatever the catchment area we have, what would be the highest amount of water that we can collect? So this is the achievable amount. So our observation is that during winter, the supply does not meet the demand. And during summer, supply is way more than demand. On average, the year-round demand is possible to meet because it's less. And the surplus water from summer can be stored for winter uses. So if the demand here is 2,800 and we can have at least 3,000 gallons. So there is in every month, if I consider 200 surplus water. So for 7 months, if I can store that water, there will be 1,400 surplus water. And for 5 months of winter, there is shortage of about 1,700 gallons of water. So this will still need a 285 gallons of water, which is short. So in overall consideration, 1400 plus 25 is about 1700. So if the recommendation is addition of a 2000 gallon tank. If we have that, have this 2000 gallon tank additional, then we can store this water from summertime and supply it in the winter time. Then we'll have a year-round availability of water. So the hypothesis 5 of that, if for every location and demand, the optimum size of rain harvesting system and AWG can be calculated, we accept this hypothesis. So my conclusion is rainfall alone is enough to meet the demand with bigger storage capacity for San Marcos, Texas. We actually don't need the AWG. So, but for other places, it might not be the case where rainfall might not be this much. This is a feasible and adaptive system, and because this saves energy and labor, and it gives better nutrition control with the purest water. The design and scale depends on definitely the precipitation, atmospheric condition, available roof area, tank capacity, the energy price, and associated risk of energy shortage. The areas with a year-round extreme weather might not be suitable for this system. So there is potential for future work and something like an efficient approach for the design parameters, sophisticated data collection method, systematic economic analysis for like water cost, investment, depreciation, break-even point, investigation of an integrated rainwater harvesting system, AWG, and municipal water system, and application of upgraded technologies such as wireless technologies, cloud data collection, rain forecasting database decision is good choice to include in the future work. So that concludes actually my presentation with this post-graduation plans I have. I have a conference in Las Vegas, CSC20 to present, and then IIC conference in New Orleans at the end of this year. And I'm currently doing the internship at Tinker and Razor. It ends at August 8th, then start my doctoral program. As you already know, these are some dates that I have to keep in mind. And these are the references. Thank you everyone. That concludes my presentation. I appreciate your time and patience for this whole time. Any questions?